Hello and welcome to a video on MOSFET DC characteristics. In this video we will have a look at the current and voltage characteristics of a MOSFET and also the nonlinear relations between the voltages and the currents. Right, the first thing you should know about the MOSFET is that it's a voltage controlled current source, unlike the BJT, which is a current controlled current source. Right. The gate source voltage controls the drain current. Then the drain and source current are equivalent since there is no gate current input. The gate is somewhat like the base of the BJT. It has infinite input impedance, so no current are flowing in. And therefore we don't have any losses in inverted commas like we had with a BJT, where those two currents should be summed to get the emitter. Now the two are just always the same, and the gate current is truly zero, and that will make most of your mathematics very simple. Right. With a BJT, we had to determine the collector and collector emitter voltage. For the MOSFET, that will be the drain current and the drain source voltage that we need to determine. And we will also do this for modeling it as amplifiers. Then the relations, the drain current is controlled by the gate source voltage, as I said earlier, and this is very similar for the NMOS and the PMOS. Now, they do react very similar. So in most of the cases, we are only going to look at the NMOS since the PMOS does exactly the same thing. So just be aware if it goes for a NMOS and there's nothing mentioned, it probably goes for the PMOS as well. And lastly, the MOSFETs are not temperature dependent like the BJTs was. Right, so first let's have a look at the construction of the MOSFET. So basically we have a doped region and then we can call it two poles. MOSFET is actually a 4-terminal device, and typically the body connection and the source connection will be connected to one another and just called the source. Now the gate and source here is what controls the current flow. Okay, so there is a bit of a thick oxide layer here and then metal on both sides, making this a very interesting kind of capacitor. So as the gate source voltage gets applied, this region here can start to conduct current from the drain through to the source. Okay, and for that we need to cross a certain threshold voltage that will be called VT in the coming pages. So a threshold needs to be crossed, then current can start to flow, and at first this will be very ohmic, this region, and then it will start to flow very freely as the gate source voltage increases. Okay, so since this is dependent on a capacitance of some sort, we have Cox, which is the oxide layer here and its thickness, and that will give us our capacitance. And if we multiply that with the mobility of the electrons in this region, we can get our MOSFET's transconductance. Now this is amps per volts squared. So that is our MOSFET's transconductance, and this is for processes scalable with the width and the length of the transistor. So you can make your transconductance larger or smaller by scaling the widths and lengths of a transistor. So this is kind of similar to the beta value of a BJT, where that was the current gain. This is kind of a transconductance gain of the MOSFET. Right, so note that big Kn is then small kn multiplied by the width and length. And this one is the one that you will typically find in a data sheet or a SPICE model of a transistor, since this is typically a secret if you buy a transistor off the shelf. So you will not know what small kn and the width and the length is of a transistor. So some of the things that they typically will give you is Kn and the threshold voltage or Vt. Right, so first important equation is the transconductance of a MOSFET. It's not the transconductance of the amplifier. Right, so first let's go over to the NMOS characteristics. Your NMOS will have three regions: the cutoff region, the triode region, and the saturation region. Okay, so saturation and cutoff is where you will use it as a switch, or the saturation is also where you will be using it as an amplifier. Note that the saturation region is not the same as the saturation region of the BJT. For the BJT, that is when it is fully on in a switch application. And we have something called the triode region. So that is when your MOSFET kind of acts like a variable resistance. Okay, so let's look at the symbol first before I go to the previous slide. And VGS is sitting here between the gate and the source. And as we adjust this voltage, more current can flow, and we have some relation to our drain source voltage right here. Okay, so if our gate source voltage is smaller than our threshold, our transistor will be in cutoff. It will be off. Right. So as we increase our VGS voltage, our amplifier will be kind of in this triode region right here. But for this characteristic, they were using the drain source voltage, or adjusting the drain source voltage and keeping the VGS kind of fixed. Okay, so for this setup, I use the VGS of 2.5 volts. Our MOSFET has a threshold voltage of 1.5 and a transconductance of 10 milliamperes per volt squared. Okay, so notice as the VDS voltage gets increased, we have this kind of non-linear graph here. This is the triode region. Okay, and that is when VDS is smaller than VOV. Now, VOV is called the overdrive voltage, and that is just the gate source voltage minus the threshold voltage. Okay, so VGS minus VTN is 1 volt. So the moment that our drain source voltage reaches this 1 volt, the graph kind of stabilizes at a specific current. Okay, now that is where our drain current. And this happens when our overdrive voltage is 1. Okay, so VGS minus VTN. So it happens at the overdrive voltage. Okay, then beyond that is the saturation. So this is the three regions of our transistor. So we should always ensure that if we want to build an amplifier, that our drain source voltage is larger than our overdrive voltage. That is one of the requirements. Okay, so to be in saturation. If it's smaller, you are in triode and your amplifier will be very non-linear. And obviously you need to be above your threshold voltage. Alright. So if our gate source is smaller than our threshold, our drain current is 0. For the triode region, when our drain source voltage is smaller than our overdrive, we are in the triode region and we have some complicated looking equations, which is not so bad if you look closely. We have our transistor parameter, the transconductance, the overdrive voltage, which is our gate source minus our threshold. So this is to ensure that we are not in cutoff, and then you just subtract your drain source voltages, half of it, and multiply by it, and this gives you your basically variable resistance. Okay, so this is when your amplifier or MOSFET reacts like a variable resistance. If you get in the saturation region, or when VDS is larger than our overdrive voltage, our amplifier, we can use it as amplifier then the drain current is half times the transconductance multiplied by the overdrive voltage squared, or the larger equation if you want to include the width and the length, or write out the overdrive voltage in terms of VGS and VTN. So this equation here is the one that we will be using mostly, since we are going to assume that we are in the saturation region because we want to build some amplifiers. Right, so this equation is not that scary at all. If you look at this, VGS must just be larger than VTN, so the transistor is on, and our drain source voltage needs to be larger than this voltage right here to ensure that we are in the saturation region. Right, and VTN and KN, big KN, is transistor parameters. So we control ID with VGS. For the PMOS, the threshold voltage of a PMOS is typically a negative voltage. So you will find that everywhere they include it in absolute values, and then they still do the subtract in all of the equations. So in short, all of the equations is exactly the same, just VTP is taken as an absolute value. So VTN is a positive value and VTP is usually a negative value. If you make it a positive, you can use the same equation for the NMOS and the PMOS. Okay, just note that typically the PMOS will be used the other way around. Our drain current is flowing from, well, it typically depends on your construction, but here's the source, here's the drain, and it will flow out on that side. Gate current is 0, and the SG is sitting up here. Okay, and that is it for our DC characteristics of our MOSFETs. In the next video, we will look at how to bias a MOSFET. Thank you for watching.